As promised, we're back for climate. What you're going to notice right now, this is going to be the last set of videos that I'll be able to do from the classroom. That's right, unfortunately I won't have this wonderful studio with my studio audience giving you the information as it happens. Alright, let's get to the real stuff. So today will be the end of my string of videos using the smartboard. I'll find some other medium for us to be able to handle future topics, but let's see if we can get through about 5 or 6 videos today. So, climate. Unlike weather, climate is an average of temperatures, an average of moisture over the course of a year, a decade, maybe several decades for one location. So when we call a place a desert, we know it's a desert because we've observed that there's very low amounts of moisture. There tends to be very high temperatures over the course of an entire year, an entire decade, maybe a whole century. So our climates are directly rooted in long-term correlations with those variables. So let's talk about a couple things first that help us understand why certain areas have different climates. If you'd like to, feel free to try to answer this question on your own as a stop and jot. So if you want to pause now, feel free. If not, let's dive right into our first factor. So the first factor would be latitude. Typically when we think about latitude on our planet, we're thinking about the big places on this planet. So we're talking about places like the equator, that line of latitude. We're talking about the poles for latitude. We're talking about maybe the tropic lines, the Tropic of Cancer in the north and the Tropic of Capricorn, Capricorn in the south. Both of them 23.5 degrees, but Cancer is in the north, Capricorn is in the south. If you do have trouble remembering where those things are, don't forget you can find them on your world maps, as well as the Arctic and Antarctic latitudes that are very important. Our circles up there. All right, so when we tend to move to higher latitudes, we tend to have generally cooler temperatures on average. As we move lower in our latitudes towards the equator, we tend to have average temperatures that are warmer. All right, so let's stop and jot in your own words here why you think polar regions are colder than equatorial regions. It's not directly based on what I said, but you can start to think about how much sunlight might hit those places. That's going to get us into that will get us into a future topic. So try to hypothesize before we get to the answer later in a few topics. Elevation. If we're talking about mountains, we've seen pictures of mountains where there's snow on top of mountains. Clearly there's snow up there because the climate is different than it is at the base of the mountain. And as we know, temperature decreases with elevation. So we would expect those average temperatures to be lower. An example, it's the reason why you can be near the equator in Ecuador and the Andes can have snow in their mountains. So if you want an example, feel free to look that up and you'll see snow-covered mountains at the equator. Nice little stop and jot moment here to remind yourself why it is that we even have snow at the top of mountains and what happens based on temperature and dew point being close together. Okay. So let's talk about how large bodies of water impact the climate of an area. So for us, we have a very intimate relationship with the ocean being right outside our front doors, and that water having an impact on the temperature and moisture conditions where we live. So for us, we know that water has a high specific heat. So if you need to, go back to the atmospheric energy videos so you can understand what specific heat means. But what we're really saying is the water in the ocean takes a long time to warm up. It's slow to cool off. So that means if you're near the water in the summertime, temperatures may not get as hot as they do in the desert. In the wintertime, temperatures may not get as cold as they are in the northern plains of the United States and the Dakotas, because that water retains that heat over time. Ocean currents specifically may also be transporting warm fluids up to different regions of the planet. Let's take a look at our oceans map. So in our oceans map, we have two different temperature currents. We've got the warm currents down here being the dark, solid black arrow, and we have our cool currents with the hollow open arrow. All right, so those will indicate what is hot, what is cold, or what is warm, what is cool. So if we are focusing predominantly on us, let's zoom in to North America. Let's get an eye on approximately where New York is, this area here. We're influenced by currents that move up the East Coast. And the most important current is named the Gulf Stream current. That current is what brings warm water from the tropics up towards us. And that warm water here helps influence our temperatures. Again, it keeps us slightly cooler in the summer, and it keeps us slightly warmer in the winter. All right. As you can see, this water moves, and eventually the name changes as it traverses the Atlantic Ocean. You've got the North Atlantic Current bringing warm water over to United Kingdom and Europe. Eventually that warm water makes its way up into the Norwegian Current. It may not be really warm compared to what we have here, but it's definitely warmer than the water coming out of the poles. So if you notice, you've got some currents in here that are moving mostly south out of the polar regions, and they are cold. So you've got your Labrador Current, you've got your East Greenland Current coming down out of the poles, bringing more cold water with it. Okay? Now, I like to kind of show the cold water current on the west coast. So here is the California current that's coming up out of Alaska. As warm water is moving into this area, cold water is moving out of that area. California coast, a lot of times you see a lot of surfers, they're wearing wetsuits. The reason why they're wearing wetsuits is this water tends to be on the cooler side. And we know that being cool water or cold water, for that matter, any water that's lower than our body temperature could impact us in terms of hypothermia. So you see a lot of surfers out here on the west coast that are wearing their wetsuits so they can retain that heat in this cooler water but still enjoy those waves. You can see there are currents all over this planet. And in some cases, we have some very small currents that kind of hide within the larger systems. So we've got this Agulhas current here, which is a little bit smaller than our larger South Equatorial or the Equatorial Countercurrent, the Antarctic Circumpolar Current. These little ones, I'll tell you, just for test-taking purposes, they like to find those little ones and kind of sneak them into your questions. With that said, when they're trying to sneak them into your questions, they tend to sneak them in by giving you a latitude, okay, and a longitude to solve that. As a reminder, this is the prime meridian here. Okay? The equator is here, but everything to this direction of the prime meridian is east. Everything until you hit 180 degrees. This is going to be the western hemisphere. And we continue the eastern hemisphere until we reach 180 again. And the reason for that is so that we can see the Pacific Ocean in its entirety, and it matches the Pacific Ocean in its entirety here as well. And the significance, again, why they did that is because they wanted to highlight the ring of fire on the Pacific Ocean, or around the Pacific Ocean. Okay. So keep in mind, if you're looking for ocean currents, you're coming to this page here, pay attention to some of the smaller ones that might show up on our exam. All right. Now, sometimes in New York State we have special conditions like lake effect snow. And lake effect snow is very unique in that you need a large body of water that's a lake. It could be an ocean depending on what part of the world you are, but for New York State purposes, our Atlantic Ocean, our Long Island Sound tends to not favor this condition because it's too warm here in the water. And usually our air temperatures don't dip low enough to use the sound or the ocean as a moisture source to create lake effect snow. the ocean tends to create our nor'easters, the really big snowstorms. So areas of colder water coming out of maybe the summer will fuel and evaporate water vapor into the air, and you might get cold air coming out of Canada that picks this up, causes it to condense, and it starts to snow in those regions. And so let's go to our New York State map so we get a better idea of what's going on here. We have a couple of major lake systems here. We've got Lake Erie, we've got Lake Ontario, and normally we've got these CP air masses that will come down out of Canada towards the early winter, maybe midwinter, and that cool air blows across this lake, and this lake has water evaporating. Eventually it picks it up, and it causes there to be a lot of lake effect snow in these regions, even over here too in Watertown, because we do have systems that do go across the lake this way. But here, this is called the snow belt in New York State. Tons of lake effect snow. Yours truly has had plenty of personal experience, and maybe if you're watching this video and you're not even part of this high school, you might live in one of these regions and experience the lake effect snowstorms on a regular basis in the winter time. And this year was no different, even though our region down here in New York City wasn't receiving a lot of snow this year. There was certainly a good amount of snow that dropped in the snow belt this year. Maybe a little below average, but certainly had its impact. So we have this air that moves across our big body of water being the lake, which might be a little on the warmer side compared to the air, picks up that air, it wrecks into the air, and then creates snow bands, dumping lake effect snow in these areas. Stop and jot. Here you've got a question here. Pause the video, give this one a shot, see how far you can get. All right, we talked a little bit more about ocean currents than I needed to before, but that all applies to here. So if you're reading through this, go ahead and read through it, but also I want you to take a moment to identify 3 ocean currents using your reference tables. So not just any, but warm water currents. Try to focus on naming at least 3. Get used to scanning the map and identifying those temperature currents. Okay, so if you had an opportunity to pause that, you gave that a shot, there's a lot of them to pick from. Anything that's going to be the solid black line, you got a lot of them all over the place, so it's your choice. All right, planetary winds. So kind of rewinding back a little bit, talking about the wind topic within meteorology, we looked at the bigger, broader picture of why winds deflect. And if you pause for a moment, I want you to go back and I want you to find that word or that rule, that law that takes place before I go ripping it out and saying it 1,000 times. So find it. All right, so the reason why we've got deflection in our winds on a planetary scale is due to the Coriolis effect. And if you went back and looked, you realize that the Coriolis effect again has to do with the rotation of Earth. And because it's rotating, that wind can't have a straight line to its location. It's going to look like it has a slight curvature to its movement due to the rotating Earth underneath the air. Okay? So our prevailing winds have names. So I'm going to quickly explain to you that you want to remember that all storm systems, all major storms and pressure systems, they like to track from the southwest to the northeast. So now, remember, we refer to winds from where they came from. So these planetary winds are called southwesterlies. Let's get to page 14 of the reference tables. All right. Let's go through. So in the reference tables, they don't tend to give you a lot of writing to read. I digress. They give you a lot to read, but they don't put it in this paragraph format. So what I'd like to do is I'd like you to take a moment to read through this with me, planetary winds and moisture belts in the troposphere. So the drawing on the right shows the locations of belts near the time of an equinox. We'll learn more about what an equinox means when we need it. The locations shift somewhat with the changing latitude of the sun's vertical rays. So what that means in plain terms, before we practice more with that, during the year the sun appears higher and lower in the sky due to our tilt of Earth and where we are around the sun in our orbit. So in the northern hemisphere, the belts shift northward. In the summer, they shift northward in the summer and southward in the winter. So if we're looking at this belt here, this is the belt they're referring to. Here is a belt. They move more northward in the summer and they will move slightly southward in the winter. Okay? And in transition during our equinoxes, being spring and fall, they're approximately here. So this picture is showing the belts, all these different jet streams, which are the belts, at these locations. So let's try to analyze this diagram a little bit more. All right. So nice, big, and beautiful. Hopefully it's coming out pretty well in the video right now, but we've got several regions that indicate to us different climates at these latitudes. Okay? Not only do we have different climates at these latitudes, but we have planetary winds that influence the weather that moves across these latitudes and these climates. So here we tend to have very dry climates. Very dry climates. So these areas tend to be, and you can label this with me, they tend to be deserts. This area down here tends to be a desert. This area here, where it says wet, tends to be things like rainforests. That makes sense when we have the equator. We have a lot of rainforests, like the Amazon. We have places that are near the equator, like the Congo. Okay? So Indonesia, parts of India are all a jungle and very close to the equator. Let's move over here so we can understand why these regions tend to have the moisture characteristics that are associated with them. So if we look here, we see as if this is the surface and you're looking outwards. So we're looking outwards. The air here is rising. And as it rises, it wrecks. So we get large systems of rain here. And it rains a lot at this latitude. If it's raining itself out, that means over here you've got drier air. You have drier air here as it moves away in this convection cell. And that dry air that's cold up top starts to sink down and it warms up a little bit. So you end up getting some warmer, drier air. Not necessarily hot. It does depend on the region. If you're in the continent away from water, you tend to be a lot hotter. So maybe you end up with some warmer, drier regions. You may end up also with some hot, dry regions. So you get some moderate to severe deserts. You may have something like the American Southwest, which is dry, but it's not as dry as the Sahara, which you have a lot of dry land away from water. These same properties exist here when you're looking at the air rising near 60. So you tend to get more snow in these regions. 60, that's up near Alaska, so there's going to be a lot of snow. Northern Canada. Siberia is a bit on the lower side. I think Siberia, you're talking more like Arctic Circle, northern Russia. You're going to have a whole lot more snow here. Same idea. Moisture falls out here and you get cool, dry air that ends up falling right at the pole. And yes, technically, the poles sort of constitute a desert. There is water available. It's in the form of ice. However, the amount of moisture that falls in these regions, the polar regions, tends to be very low like a desert. But that small amount of moisture doesn't disappear because it's cold. So it starts to build up all of that snow and continues to create maybe more glacial ice on top of what was historically an ancient ice that built up in those regions. Back to just reminding ourselves that here we have our southwesterly winds. This is the area we live in, between 30 degrees north and 60 degrees north, blowing to the northeast, coming from the southwest. These winds that are below 30 degrees south, areas that are, Mexico, Central America, northern South America, you've got winds that are coming from the northeast, and they're blowing to the southwest. Those same or similar those similar ideologies work down here as well that we have, but they're the opposite direction in the southern hemisphere. These jet streams are typically the very fast-moving fluid air in the upper atmosphere that's moving our systems across the United States as well. And you have several. You've got your polar jet stream, you've got your subtropical jet stream, you got another polar jet stream up here as well. Okay? And this dashed line is representing the tropopause, where all of our weather takes place beneath that altitude. All right, so now I'd like you to give these two questions a shot. If you need to, go ahead and pause the video and try these out, and we'll be back shortly, which will be right now, in case you didn't pause. But if you did pause, we're back. So, these two questions here, we've got which combination of climate factors generally results in the coldest temperatures? So what are our options? What factors are we dealing with? We're dealing with elevation, and we're dealing with latitude in each of our choices. So if you needed to, you went back in your notes, you drew a comparison between your notes and applied it to this. So if we're trying to figure out where it's cold, high elevation, top of mountains, yes. High latitudes, close to the poles, 90 degrees north, above 60 degrees north, and above 60 degrees south. Choice 4. All right, question 2. I'm going to have to zoom out. Question 2, rather significant. So we've got here figure 1. Base your answer to this question on the passage and the data table below and on your infinite knowledge of Earth science. The data table shows monthly average high temperatures in degrees Fahrenheit, the monthly average snowfall in inches at the summit, that's the top, it defined it, of Mount Washington in New Hampshire. We're on a mountain. You gotta start thinking about different aspects of mountains. Mountains are metamorphic. Mountains have uplift. Mountains could be volcanic. Mountains are high elevation, so they're cold at the top. Mountains create a rain shadow. You have orographic effect. All these different things you have to start thinking about with mountains. Right? Let's read. Mount Washington, located in the state of New Hampshire, is one of the highest mountains east of the Mississippi River. This mountain, as well as many mountains across upstate New York and the Northeast, has deep-cut glacial valleys formed by continental glaciers approximately 1.7 to 1.8 million years ago. Hurricane force wind gusts are observed at the summit, again, the top of Mount Washington, on an average of 110 days per year, including a record wind speed of 231 miles an hour. It also receives very high levels of snow. It averages 282 inches. That's 23.5 feet of snow per year. Here we have a data table. We have a title, Mount Washington monthly average high air temperatures and average snowfall. So we have our months. We have one full year of months. We have the average high temperature in Fahrenheit. We have the average snowfall in inches. So we've been given temperature and moisture conditions. Question. Identify the climate factor that best explains why Mount Washington has relatively low air temperatures throughout the year. Well, we can take one of those initial things we should remember with mountains, and we start to say to ourselves, mountains, high elevation, higher elevation, it's colder because the air is expanded, so therefore that's why it has relatively low air temperatures. You could also just briefly say higher elevation has lower temperatures. Anywhere within that range of answers for specificity purposes should be more than sufficient to explain this concept. All right, so we have reached the end of this episode. Hopefully you've been able to gain some new knowledge after reading through this. You're practicing your independent practice questions. Go ahead and leave a question down in the comments below. Feel free to message me in Jupyter, Google Classroom, and hopefully we can maybe meet together on WebEx and make sure that we can come to some understanding together. So go ahead, start your independent practice, use your access points, check your answer key, and we'll see you later. Bye.